Good afternoon, everybody. So I have absolutely no idea what Faisal said about me. It could have been anything. So first of all, I'd like to say a big thank you to Faisal for inviting me to come and share some of our latest results with you today, and also for the Turkish Society or Association for Psychopharm. I'm the President-elect for the British Association for Psychopharmacology, and I'm very excited to see the lively collaboration between the two societies. The other thing I need to thank Faisal for is for lending me her very talented PhD student, Jeren, last summer, who came to our lab to set up one of the novel tests I'm going to talk to you about today. So I'm going to be able to show you some of her results. Thank you very much, everybody. Okay, so I've come all the way from Manchester. I have to tell you the weather in Manchester is not quite as good as it is here, so I shall be very sad to leave here. Manchester is quite a famous city. I'm sure many of you have been. It's a northern university city, north of England. We have very well known for lots of music. Apparently, I know nothing about football, but apparently there are two very large competing football teams, the red one and the blue one. I hear the blue one is doing slightly better than the red one, but I might be mistaken. Manchester University, that's where I'm located in the School of Pharmacy. It's the biggest UK single-site university. One of the most exciting things about Manchester, though, we have the highest number of Nobel Prize winners on our staff, including these two Russian physicists, and they discovered graphene. I don't know if you've heard about graphene, but it's as thin as cling film and as hard as steel, and they're finding more and more uses for graphene all the time. And particularly exciting for me is the fact that they make sports rackets out of graphene, and they make squash rackets. I'm a squash player, and tennis rackets. So I play with the same kind of racket as Djokovic and Murray, and I have to tell you my squash has improved massively since I've started playing with this graphene. Okay, so 3 issues really to cover with you in the talk today. I'm going to start by talking, because I'm a preclinical scientist, so my research is animal models, developing animal models of aspects of psychiatric conditions. So I'm going to spend 5 minutes at the beginning just talking to you about some of the key issues associated with working with animals in the laboratory and validating translational animal models, so animal models that are meaningful for clinical conditions. And if we can't do that, there is no point in doing it. It's very important. So that's the first aspect. The second part is about the animal model of schizophrenia symptomatology, particularly cognitive deficits and negative symptoms that we've set up in our laboratory. Then I'm going to talk about new tests that we've established in our lab for aspects of negative symptoms. This is using rats. And thinking about the different domains of negative symptoms. So thinking about the avolition domain, so lack of drive, lack of motivation to get a job, to have a relationship, to get up in the morning, to go out, to do anything. So that's a really serious situation for schizophrenia patients that's holding them back from leading normal lives. So that's one very big aspect or domain of negative symptoms. And being asocial or not being good in social situations, not having good relationships, forms part of that. So, and we can study that in rats, so I'll be talking about that as part of the avolition subdomain. And as part of the expressive subdomain, I'll be talking about 2 new tests we're setting up to measure affect or mood in rats. And I hear you saying this cannot be done. Rats do not have different moods. Rats are not happy or sad, but we can measure, if we're very careful about it, affect, an affective state in rats, and this is part of the work that Jeren's been doing with us. And clearly, for adding on new targets for cognition and for negative symptoms and even new antipsychotics, there have been a lot of very disappointing results in the clinical trials, with some very big failures that we'll talk about. And so at the very end, I'll try and consider a little bit why these targets have worked in the animals, or in the animal, some of the animal tests, but not then in the clinic. So just to explain what B-Neuro is, because you will see this logo, so, and just to try and put me into context for you and the work that we do and the experience that we have. So it's a small contract research organisation whereby we as a team test new drugs for the pharmaceutical industry, but these are usually add-on drugs for cognitive deficit symptoms and also working on negative symptoms. So I have tested practically every target that's gone into phase 1, phase 2, phase 3 clinical trials, the glycine uptake inhibitors, the glutamatergic drugs, the alpha-7 modulators, ampakines, the serotonergic drugs, the dopaminergics. So I have a lot of experience of working with a lot of different targets. So just to consider animal models for a minute, not these kind of animal models. So actually there are two features of developing animal models properly in the laboratory. And the first of these is understand your species and really get to know your species very well. And so you're mainly psychiatrists, so your species is humans, the human primate, and you all will know your subjects very well. And I think this is maybe one of the problems with the animal model development, is that people really don't understand the species that they're working with well enough. So really you need to be an ethologist, so you need to understand the natural behaviour patterns of animals, how they behave in the wild, what their feeding patterns are, what they're frightened of, what they like to do, what behaviours they like to engage in. So really I can't stress this enough, that this is one of the most important aspects of developing the animal models, is to understand your species and to develop in the laboratory appropriate tests so that the animals are engaging in behaviours that are natural for that species. And every species is different, and rats and mice are actually very different. They may both be rodents, but mice are highly aggressive and territorial, and rats are not. They're much more sociable, and they live in big colonies in the wild. So that's a very important aspect of this, very important to get that right. And the other aspect then is the illness, the human condition. This is all about trying to simulate what's going wrong in humans using an animal. So the more we can understand, the more I can gain from your experience about what causes the psychiatric conditions, what is the pathophysiology of those psychiatric conditions, and what are the behaviours, because psychiatric conditions are all about disturbed behaviours. So for us it's studying the behaviour, the appropriate behaviour in the laboratory. So that's where construct validity comes in. You really have to try and construct the illness, the human illness, in the animal as best you can for the cause, the pathophysiology, the behaviours. Your animal, you have to understand the behaviours, as I said before. That's kind of where face validity comes in. But I want to just focus on predictive validity for 1 second, because one of the aspects of developing or validating your model is that the model should or is supposed to detect or show efficacy of drugs that work or exist in the clinic. Now, I think this is a particular caveat, and in fact leads us to has led us down the wrong, in the wrong direction. Because if the drugs that existed in the clinic were good enough, were so good, then we wouldn't need the animal models to develop better drugs. And actually what we need is drugs with a different mechanism of action, hitting different targets. And if the model is being designed only to pick up, for example, D2 blockers for schizophrenia, that model or test is not going to pick up novel targets. So I think validating your model using drugs that exist in the clinic is not a particularly helpful aspect of animal model validation. Okay, so I'm not going to go on about this anymore. Just to summarise, it's very important to understand your species and to really get to know the species that you're working with. So whether it be, I've worked with rats, with mice, with primates, and they're all very, very different. They engage in different behaviours and they have very different habits. So be part David Attenborough. I don't know if you know what species David Attenborough is frightened of. You know, David Attenborough's studied every species practically out there. But just have a think about that and I'll tell you at the end. So think about the levels of validity, but we really need to spend, I think, a lot more time in developing and validating the animal models appropriately so that they really translate into the clinics. And I think there hasn't been enough time and effort spent on this in general. We have to, so the two things, ethology and simulating the clinical condition, and we must translate into the clinic. Okay, so I don't need to tell you what a serious, debilitating, devastating illness schizophrenia is for sufferers, for service users and for their families, and the problems with the existing drug therapy. So many patients do not have their symptoms well controlled, particularly in respect to negative symptoms and cognitive disturbances. And this is very important. Many patients still have moderate to severe impairment. And if you look at this, so the cost, this is from Robin Murray's Schizophrenia Commission, the cost of looking after patients with schizophrenia is estimated to be £60,000, British pounds, per year. And this cost is not the drug therapy, this is all the other care and the lack of that person being able to work and having a normal life, so the sort of burden to society, if you like. And this can only really be alleviated by better therapies and therapies for the aspects that aren't treated, such as negative symptoms and cognition. So as I said, we've had some spectacular, and I have to say incredibly disappointing, failures in the clinic with respect to new schizophrenia drugs, and this in particular, bitopertin, the Roche drug that was specifically developed to treat negative symptoms. So the reason I point to these two is because these two both interact with the glutamatergic system. And I think it's worth spending 1 minute just to think about both these drugs and their mechanism of action. So we're thinking, and I will talk a little bit more about this in a minute, about the glutamatergic hypothesis of schizophrenia, where the glutamatergic GABA circuitry in hippocampus and prefrontal cortex is disrupted in schizophrenia, thought to be started or initiated by NMDA receptor hypofunction or malfunction, and we will talk a little bit more about that in a minute. So one strategy is to enhance activation of the NMDA receptor. Glycine is a co-agonist at the NMDA receptor. So the strategy of the glycine transporter inhibitor, so these transporters are located on the presynaptic nerve terminal and on the glial cells, responsible for taking glycine back up into the neuron. So if we inhibit that, we increase the availability of glycine for activation of the NMDA receptor, and that was the strategy of the glycine reuptake inhibitors or transporter inhibitors. And we have tested a great number of those. Most pharmaceutical companies did have one that we tested. So that's one strategy. The other strategy is this NMDA hypofunction ultimately leads to glutamatergic hyperfunction and too much glutamate, and too much excitability is a bad thing, can cause progressive neuronal degeneration. So the strategy of the Lilly compound, the glutamatergic agonist, again, these receptors are located on the presynaptic nerve terminal and on the glial cells and are responsible for transporting glutamate back up into the neuron. So these were stimulated. So this is an agonist, this Lilly compound, activated by the compound and increases the reuptake of glutamate back into the neuron. So it reduces this pathological glutamate release. So this was two different ways of targeting the glutamatergic system. And their failure has, I think, led to a lack of confidence in targeting the glutamatergic system. But hopefully, by the end of today, I will have restored your faith in this, because I'm going to talk to you about a new target that targets this system, but in a completely different way and using a completely different mechanism, which is where sort of my point about the animal models finding new, completely novel targets comes in. But this very, very large GWAS study that was published in Nature last year, massive amount of schizophrenia patients, over 36,000, identified a lot of risk factor genes for schizophrenia, in particular, as you would expect, the dopamine D2 receptor gene, but also those involved with glutamatergic neurotransmission. So clearly it is at the core of the illness. And I just want to highlight this as well, so genes involved with immunity, and highlighting the importance of understanding the interaction between the immune system and schizophrenia. And I think Peter Haddad's going to talk a little bit about the anti-inflammatory molecules that have been tested for negative symptoms, the NSAIDs, minocycline, and so on. Yeah, and I'll mention that at the end. Okay, so to the animals then, and to trying to model, or sorry, trying to test aspects of negative symptoms in the animals. So I've done a lot of work on cognition, and my strategy for cognition has been to have a different test in the animals for each aspect of cognition that's impaired or affected in the illness. So an attentional set-shifting task for executive function, a different task for vigilance, object recognition for visual recognition memory, and to test the targets or the new drugs in each of these tests. So that is the test. Well, just to point out that there was an edition of European Neuropsychopharmacology came out last year, all about negative symptoms. So if you're interested in negative symptoms, which I'm guessing you are because you're here, that is well worth a read. Okay, so I'll try and take you through this cartoon to explain to you the glutamatergic theory of schizophrenia. So the hypothesis is, as I said, that the NMDA receptors are dysfunctional. Now, these high-affinity NMDA receptors are located on these fast-spiking GABA interneurons that contain parvalbumin. Parvalbumin is very important. So the calcium-binding protein parvalbumin, and I will come back to that. So GABA is the inhibitory neurotransmitter. So essentially, because these NMDA receptors are hyperfunctioning, you're losing the inhibition, the inhibitory control that GABA has over subsequent glutamatergic neurotransmission. So those interneurons synapse with the glutamatergic receptors on the pyramidal cells, and you lose inhibition. So you've got a disinhibited circuitry. And those pyramidal cells are responsible for synchronized activity in this hippocampal prefrontal cortical network, which is essential for cognition, controlling gamma oscillations. So you have a desynchronized, disturbed, disinhibited system. And those two drugs that I showed you, they're ways of interacting or trying to normalize that disturbed system. Now, I want to point you in the direction of this target here. These potassium channels, Kv3.1 channels, are bang on. They are located on these GABA interneurons. So that's a potential target for modulating activity of this, this system, kind of where the disturbance starts. Those Kv3 channels are also located in the VTA, the site of projection of the dopaminergic neurons. So they are absolutely in the right place for normalizing transmission that's affected in the illness. So my model, I've talked a little bit about tests, but in the animals we have to try and recreate the human condition, so the pathophysiology of the human condition. And I do this by treating the animals with PCP, an uncompetitive NMDA receptor antagonist. So we're inducing an NMDA hypofunctional state in the animals. I give it to adult animals. I use female animals because they're a lot smarter than males, and I'm interested in cognition, so all the women in the audience will know this. They're adults, so this is not a neurodevelopmental model, and it's got no genetic components, so it's certainly not a perfect model, but it does recreate the pathophysiology and the cognitive and behavioural disturbances very well. So the really crucial thing to understand about this is I give these animals PCP for a week. They're adults, they get it twice a day, a relatively low dose, and then they never receive PCP again. So that's the absolutely key thing here. So you have induced an NMDA hyperfunctional state that has caused very, very long-term neurobiological deficits, and I can tell you we get a very nice parvalbumin deficit in these animals, in hippocampus and in prefrontal cortex. And it's very stable cognitive disturbances. But the thing to remember is when I'm testing these animals, there's no PCP on board, so you don't get any compound out of an NMDA blocker or amphetamine on board affecting the animal's behaviour. So they're completely drug-free apart from the drugs that I am giving them, the novel targets. So I've been working on this model for a long time. As I said, this is not for the faint-hearted. Developing an animal model takes a long, long time and effort. So maybe 15 years I've been working on this model. So we get very selective cognitive disturbances, and as I said, different tests for each domain of cognitive function or dysfunction, and a number of neurobiological changes, including reduced grey matter density in the infralimbic cortex, reduced cortical thickness. But it's the parvalbumin I really want to focus on today because of the effects of the Kv3 channel modulator on parvalbumin. In fact, I brought a poster with me. So I'm going to show you a little bit of data now. Obviously, I talked to you about the Kv3 channel because I'm working on a Kv3 channel project in collaboration with Universities of Newcastle and Tiffany, the company that have made these molecules. So these are Kv3 channel modulators, and I'm going to show you what is, I think, some very, very heartening and exciting data, certainly in view of the failure of the glutamatergic molecules in the trials. First of all, I'm going to talk about social behaviour, social withdrawal induced by the PCP. So we're a highly social species. Look at you all. You're all sitting very close to each other. We've had lunch together. We'll probably be having dinner together. You live in family groups. Rats are the same. They're a highly social species. So just to reiterate how we do this, I treat my female adult rats with PCP 2 mg per kilo twice a day, 7 days. They never get it again. And these rats, the data that I'm going to show you, these rats might have been tested as much as 6 months post-PCP. And in fact, the deficit lasts for up to a year. So I want to show you, to give you a bit of a feel. Thank you. We're like a double act. Thank you very much. For what kind of work we're doing. So these are 2 normal rats, but they've never met each other before. So they have to meet, they have to shake hands. Hello, how are you? And there is quite a lot of social interaction, so anogenital sniffing, behaviours that are relevant for that species, following, sniffing, and general interaction. So I just wanted you to get a feel for how we do this kind of work, because I think it's quite hard to really understand it. So they're weight matched, so there's no aggression, no stress. They're used to the arena. They're just not used to each other. So those are 2 normal rats, control rats. They haven't had any drug treatments. Now here, this is a PCP-treated rat, and it does not really want anything to do with the other rat is a normal control rat and hasn't had any PCP. But there's no fighting or anything, but the PCP rat just very politely ignores the other rat when it comes up to say hello. So we get social withdrawal and we score the behaviour of the PCP animal. This is quite a lot of work, actually, to score these animals. But I talked to you about this Tiffany compound, and I said we've been working on it for a little while now. So we had a collaboration that's just about to finish, and we have a new 2-year collaboration starting, funded by the UK government and Tiffany. And just to show you a little bit, I'm not going to bore you by showing you a lot of data, but this is very exciting, I think. So these are the normal rats, and they sniff one another. The PCP animals show a withdrawal, so you get reduction in sniffing and an increase in avoiding behaviour. And this is normalised. This is the Tiffany compound, the Kv3 channel modulator, AUT6, normalised by this molecule and also by low-dose risperidone, 0.1 mg of risperidone. Having said about predictive validity and not testing, not having to show drugs that exist in the clinic, I'm as guilty as anybody else. But this is a very low dose, not a D2 blocking dose. So what about the other compounds that I talked about? Bitopertin then also, there's the deficit. Normal rats, PCP, sniffing. Bitopertin only at 1 dose, so at 10 milligram per kilogram, which is a higher dose than the equivalent was tested in the clinic. So bitopertin works very nicely and also works to restore cognitive deficits as well. This is the cognitive deficit in the PCP rats. This is the normal rats. And bitopertin at the same dose restores the deficit, as does risperidone. What about the Lilly compound then, the glutamatergic mGlu2/3 agonist? Does nothing. So there's the deficit, does nothing to restore it, doesn't bring it up back to normal levels. There's the avoiding, the increase in avoiding, again, does nothing. Does nothing to the cognitive disturbance either. So that was a negative for the LY compound, but a positive for the bitopertin. And a really nice effect with the KB3 channel modulator. So now this surprised me. So rats engage in this kind of rough and tumble play behavior from postnatal day about 35 to about 43. It's a very, very small window. And you don't normally see adult rats engage in this kind of pinning and pouncing and extra social behavior. And actually in this situation, I have never seen it. These are female rats. They engage in it even less than male rats. So I was very intrigued and excited to see that in these animals. And that was caused by this new molecule, the ortiphany compound, and also by bitopertin at 10 milligram per kilogram. So that's kind of taking them back to their childhood, you know. But that's something, as I said, I've tested a lot of targets. I've not seen that before, so that's particularly exciting. Now, I did tell you that we could measure mood or mood state or affective state in rats, and there are 2 different tests that we've been developing in our lab to do this, developed by, I have to say, some really clever scientists. It's not by me. The other thing you can do in animals is nest-building behavior for care, because negative symptoms are associated with lack of self-care. So 2 different tests, and you know, I know we don't have an awful lot of time, so I'm not going to bore you by taking you through all this, but I just want to show you a little bit of very early data. So this is the first test, the affective bias test, and basically rats are digging in bowls. So rats like to dig. We use smells to guide their behavior. Rats are very, very olfactory sensitive. The animal is injected with the drug, and it learns that one smell is paired with availability of food, and in that situation, the other smell, there's no food in that bowl. So it learns to associate a smell with the effect of the drug, a little bit like conditioned place preference. And when it gets the vehicle treatment, it gets the other smell. And you test so you have to condition the animals to this. And in the test situation, the animal, it's very simple. It's given a choice of smells. No drug on board at all. If it preferred the effect of the drug, if the effect of the drug was a good effect, then it will choose that smell. And if it was a nasty effect, felt bad, it will choose the other smell. So I think this is quite simple but very, very effective. The second test is the one that Jaren worked so hard all summer. This is the sandpaper test. I think this is a particularly smart test. So rats are very tactile sensitive as well. Again, we're using smells and rats digging in bowls, smells to guide their behavior. Really simple. It's so smart. So they have a high grade of sandpaper would be paired with a high value reward, and Jaren shows chocolate drops. And a very low grade of sandpaper, so something that's very smooth, would be paired with a low reward. Jaren shows Cheerios. And then what you do is you give the animal an ambiguous grade of sandpaper, so it doesn't know what's coming. And if it chooses the smell that's associated with high reward, then it's optimistic. And if it chooses the low reward, then you can say the animal has had a pessimistic bias. This is very, very smart. So just very, very early data with the PCP model. So if you do the affective bias test with high value and low value reward, all animals will choose the smell paired with the high value reward, which we all would, I certainly would. And the PCP rat doesn't induce a negative affective state, so they don't choose the low reward, but you just lose the positive bias, so it's like a lack of affect. And in the optimistic, the sandpaper test, the normal animals make a reasonable number of optimistic choices, and the PCP animals make much fewer optimistic choices. So they also have a negative optimistic bias, I'd say. So you'll be delighted to hear I've finished. I hope I haven't gone on too long. Just to summarise what I've shown you then, bitopertin and this Kv3 channel modulator restore PCP deficits in social behaviour. The Lilly compound was completely ineffective. AUT, the autophony molecule and bitopertin enhance behaviour beyond normal social behaviour, sort of taking the rats back to their childhood. We get a reduction in positive affect bias and a reduced optimistic bias in the PCP model. So obviously my next step is to try and reverse this deficit with the Kv3 channel modulator. And I've started a little bit, an AUT alone, a slightly different molecule, induces a positive bias, not again in the PCP model though. So I think the Kv3 channel is a very exciting target, very promising, and potentially could restoring function. Now we've done a 21-day study, and that's why I brought the poster with me, of the autophony compound in a cognitive task, and over 21 days it restores cognitive function. But the most exciting thing about this study is that it restores the power of albumin deficit, and I've not seen that happen with anything before. None of the atypicals that we've tested have done that. So the power of albumin is much more plastic or elastic than we actually thought. And it's possible, I mean, I guess it's not a big surprise because those Kv3 channels are located on the GABA interneurons that contain power of albumin. But when you stop the treatment with the autophony compound, then the power of albumin looks like it comes back down again. So it's not a magic cure or anything, but it does. That's the first thing I've seen to restore functionality. I think can restore functionality in that way. So very, very exciting, I think. So just to be clear, though, this is the model, the PCP model, the neurobiology, the behaviour is well validated and mimics the clinical situation reasonably well. But as I said, it doesn't have a genetic or a neurodevelopmental component. And it's just the start, because that's like testing your drug in an ultra-high risk group, isn't it? And most of your patients will have antipsychotics on board, or they will have had antipsychotics on board for a long time before they're going to get a new treatment or an add-on treatment. So these are the next studies, and that's the next money we've got for the autophony project. And I have started to do this for other clients. So you need 21 days of a D2 blocking dose of haloperidol, and then you need to add on your add-on therapy, or you need to stop that, wash out, and then really try and mimic the clinical trials, and then give a new antipsychotic. So really, we've just started, and Tony Grace has done some very, very nice work on this in his developmental model. So just to conclude then, I think to study negative symptoms in the lab properly, we have to consider negative symptoms separate domains and have a test for each domain, as we've done for cognition. The animal model should include antipsychotics. At some point, if it's add-on, you need the antipsychotic on board. If it's a new antipsychotic, you need to have had some treatment in the model with the antipsychotics before you give the animals your drug. So that's our next step. I wondered, I don't know really anything about the clinic, I wondered if patients could be stratified into different domains of negative symptoms, the way maybe we will do for cognitive disturbances. Big thank you to all the people who've done all this work, Jaren in particular. It slaved all summer in our lab doing the optimistic bias test. It looks very simple, but actually it's a lot of work to run. All the Manchester crew, the autophony people, thank you very much. I want to finish by plugging something. I know I shouldn't do this, but we're organising a symposium, a one-day symposium in an art gallery, and it's showcasing artwork by two patients with schizophrenia, and this is in Manchester on the 13th of May. So please do come across to Manchester. I'm sure the sun will be shining, as it very often does in Manchester. So I won't bore you any longer. Thank you for being very patient. Thank you all very much for your attention.